I wish to concentrate mainly on the spectroscopy of nanomaterials because much has been talked about what is a nanomaterial and how it works, how it is different from the bulk materials, and what is so special about different nanomaterials. And what comes next when you talk about research in nanotechnology is analysis of the nanomaterials. And the first and very important tool is UV visible spectroscopy. It is known as a conventional technique, but it is finding applications by and large in the analysis of nanomaterials, the electronic properties and optical properties. So one should be able to analyze the materials using UV visible spectroscopy, and the theoretical background of the spectroscopy of nanomaterials is slightly different from the analysis of conventional materials and the organic molecules, and the electronic transitions involved are also slightly different, and we should be able to explain how they differ between the molecules and the nanomaterials. So that is the focus of this lecture. And this obviously you have already seen that Lycurgus cup was analyzed in Rome. It dates back to several hundred years, maybe 500, 600 years. What's interesting about this is the coated nanoparticles, not known as nanoparticles earlier. It's a mixture of gold and silver nanoparticles. It was known as gold and silver nanoparticles when cut down to the nanometer size scale could be illuminated at a particular wavelength. The term nanotechnology was not at all used, but it was known. The application was what was anticipated out of the cutting down of materials to the nano size. With the modern tools, when they were analyzed, it was found that they had size in the nanometer regime. The modern tools analyze them with a different focus. And when we talk about nanomaterials, we mean that they are engineered nanomaterials. We talk about engineered nanomaterials. We cannot say a sub-micrometer particle just as a nanomaterial. Anything can be measured in the nanoscale, but if you are doing something in the laboratory, you should say that it is an engineered nanomaterial for a purpose. And the modern tools of analysis should be employed, justified, and we have to derive properties and tune the properties. That is the focus of the modern nanotechnology. As it involves materials, it applies in different fields. It could be applied in the optoelectronics, could be applied in biological imaging. So you understand it has application from a wide spectrum of applications these nanomaterials find. So you can say that these are materials at the nano size scale having a precision at the nanoscale, tuned with desired properties and applied. And to analyze them, we need spectroscopic tools and imaging tools. One thing one should know is the analysis is mainly through the imaging techniques like atomic force microscopy, scanning tunneling microscopy. These are all tools to see them directly and find out particles at the nanometer scale. But you can still use spectroscopic methods to analyze them. That is what is the theme of our discussion today. This is another example where the nanomaterials were identified. This is some excavation from Keeladi in Tamil Nadu, the ancient civilization that dates back to 600 BC. It was once known that the oldest civilization in India was Indus Valley civilization, and now we observe that there was a civilization that dated back even older than the Indus Valley civilization. Much of the studies are being carried out. Interestingly, these pottery had paintings which had carbon nanomaterials. I have purposely chosen the example, the Lycurgus cup and this pottery in Keeladi, because these involve gold and silver nanoparticles and carbon nanomaterials. This carbon, silver, gold, these are all household names for us. These are all very common names. And these find a huge portion of study in the nanomaterial analysis, in the nanotechnology field also. Here is Richard Adolf Zsigmondy, an Austrian-German chemist the Nobel Prize winner in 1925, he used gold nanoparticles of red color. When we talk about the color, what comes to our mind is the shiny yellow color that is pertaining to the bulk gold. But this is gold which is red in color. Any layman cannot even imagine gold in red color. These are all nanoparticles, gold nanoparticles, no paint, no polymeric color painted on that. Nothing is there but the metallic gold nanoparticles in nanometer scale. What makes the difference? Just the change of size makes the change in the color. Color is not just mentioned in the aesthetic sense. Color means wavelength. Color means wavelength of absorption. Wavelength of absorption again translates to wavelength of emission. And these are linked to the applications. These are linked to the spectroscopy. And that's very interesting. And Adolf Zygmundi did not study that as a nanomaterial. He wanted to study nanomaterials in the context of catalysis and coloring utensils. And without further insight into what the material was and why should it change color. And the modern sense of nanotechnology was there starting from 1965 when the visionary lecture by Richard Feynman was delivered. Of course, he talked about the top-down approach, what is now known as top-down approach. He was a physicist, so obviously one could understand he thought about cutting down things to small scale with lasers, with radiation. And he said such kind of writing of the entire volume of Encyclopedia Britannica on the head of a pin was not realizable. It was realizable, he said. It would not go against the laws of physics. The fundamental laws of physics would support such writings. It's not counterintuitive. It's possible to write everything on the head of a pin using modern tools. He raised the eyebrows of scientists. And from that, other people worked on nanotechnology, not in the name of nanotechnology. Again, the name was coined by Taniguchi in Japan. I am handpicking scientists because the proposal by Richard Feynman is in one direction. Of course, he had a perspective from physics. And here is one professor. He is still there. He is working in this area. He is Eric Drexler. He submitted his thesis actually on what is known as molecular nanotechnology. And he said that, being a biologist, he said molecules can self-assemble. That obviously is realized in the world. DNA is a molecule having two strands that gets connected and that carries information. It carries the hereditary information. It is a kind of coding. And why can't we make molecules that assemble like DNA molecules? It's not against the laws of chemistry or physics. That is nothing but hydrogen bonding. And if you can assemble that, there may be one scenario where you can imagine something like what you see in Hollywood movies. The molecules can multiply themselves and self-replicate. And there would be a scenario called gray goo scenario. And these are all hindsights. It's not imagination. It's a foreseen scenario. And that is again possible within the laws of science. So this is something which is just opposite to, not in concept, opposite to the way of offering nanomaterials. The way Richard Feynman proposed was cutting down larger size to smaller size, and Eric Drexler proposed assembling smaller units to larger molecules. So both approaches stand opposite to each other, and first one is called top-down approach, the second one is called bottom-up approach. That's how we can easily understand these two approaches. These are all buzzwords in the nanotechnology field. These are the first basic nanostructures. I talked about gold, silver, and carbon. Carbon, metallic gold, silver, iron oxide, cadmium selenide, black copolymers. These are all making the major avenues of nanotechnology. These are all very common nanomaterials, finding huge applications from one field to the other. You can study the weird properties of these materials in the nanoscale. What you see At the center is metallic gold in yellow color and 20 nanometer gold nanoparticles in red color, and something which is above 100 nanometer in the violet region. So you find a violet color and you find out carbon nanotubes, the scanning electron microscopic image of fullerene and carbon nanotube. The fullerene is a carbon 60 material, which is something like a soccer ball, which was invented in 1990s. Carbon nanotubes, which is the third allotrope of carbon. Once it was known carbon had two allotropes, graphite and diamond. Now we can say there is a third allotrope of carbon, which is carbon nanotube and the related stuff, meaning that fullerene and graphene. And you see the scanning electron microscopic image of the carbon nanotubes and the fullerene. You find out such a precision in the image. What you see at the left side bottom is semiconductor nanoparticles of different composition. You find colors. Colors mean wavelengths. I am coming to that. And at the center is iron oxide, black in color. Iron oxide in the bulk scale is red in color, dark red in color. And in nanometer size scale, it is black in color. And what you see at the right side bottom is block copolymers. And these materials, they find huge applications, and they are called as the five, they are the backbone of the entire nanomaterial field, nanomaterial world. Applications are there based on light absorption. See, Berkeley lab scientists have created these materials. This is a paint not made of organic polymers. These are all small organic molecules with tail and head units are there, but inorganic materials with different light absorption. And how are they applied is given here. You see, it sends back the IR radiation. It allows the visible light to pass through, and it could replace the fuel dramatically. This is the goal of the study, and it can be used for energy efficient windows. All depends on how light is absorbed. To study how light is absorbed, what kind of wavelength is absorbed and emitted, you should start from UV visible spectroscopy. I talked about the microscopy, scanning tunneling microscopy, atomic force microscopy, transmission electron microscopy. But you can start from ultraviolet visible spectroscopy. The UV visible spectrometer costs just around 4 lakhs. And it's not like nanotechnology. It's a costly technology as far as the analysis is concerned, as far as the research is concerned. And let me give another example. These are nanowires that move data at speed of light. Nothing can go past the speed of light, of course. It goes closer to the speed of light. Let me be safe in saying that. Physicists would oppose that, at least according to the conventional laws. Somebody said something travel faster than light some years ago. Then they withdraw the statement. In Europe, that something which moves data at the speed of light, nanoscale wires. And what is used here in the processing of that? Lasers are used. It's not using electrical pulse. Instead, it uses the lasers to read the data and transmit data. So electronics is just the storage, and to pass the data, you need light. So you should know about the ultraviolet radiation, visible radiation, and what comes next to the visible range is the near infrared region. I will talk about it later. Say this is some material that changes color, and you call that as a robotic chameleon skin. And it's a film made of gold nanoparticles that changes in color. So this is like an oscillating color that displays something on a screen. Okay, how the technology changes, you should know. See, it's not using a lot of big electronic equipment, a material that occupies the size of a room, a screen that carries a large number of LEDs. Everything is nanometer size scale particles. This is one application in biology, and you find the gold nanocrystals getting the light absorbed, and it eliminates in the red region. You find out red color emission, and that shows a good contrast in the live cells. Normal cells have background fluorescence. The light absorbed is emitted, and that shows a color that is pertaining to the color of the cells. And your material should be having a good contrast in the background of the normal fluorescence. You call that as a background fluorescence, and the material should absorb in the near infrared region. In the red region, let me say, the red has different tinges of color, and you find this gold nanocrystals having red color absorption, and that is showing such a bright color emission in the cells, and you find good contrast. What is the application of that? This can be used for image guided surgery, imaging cells, the transport of drugs in the circulatory system, the cellular uptake of therapeutic molecules. All these can be analyzed. Another one you find out at the right frame is carbon darts. I talked about carbon nanotubes, fullerenes, the third allotrope of carbon I said, and there is one thing called carbon dart. These are all broken pieces of carbon, and they aggregate in the nanoscale, maybe up to 3 nanometer or 5 nanometer, very small. It's difficult to analyze carbon darts under scanning electron microscope. What is best for the analysis of carbon darts is imaging them using transmission electron microscope, silicon nanoparticles that show a green color emission, and these are all materials in the nanometer scale which shows characteristic absorption. Much of the work has been done in this area, and China obviously is the leader of studies in the nanomaterial nanotechnology field, followed by USA, and happily India is also part of that. Of course, the analysis, the fundamental and applied sciences, they complement each other, and that's where the funding has to be spent. And if only there is funding, there is research. And research is not just about products. Products come later on. If somebody asks that what is the product you have brought out of your research, immediately, maybe convening a meeting or something, if somebody asks that is like reaping where you have not sowed seed. The money should be spent, the budget should be shared, there should be fundamental research, applied research, and then only there is application. Interestingly, in India, if there is a good funding, we can bring out even more products. We can bring out mainly good results that is academically intriguing, academically that kindles the academic enthusiasm of students and researchers. And then we can derive new properties and propose new theories and bring out new applications. So this is the electromagnetic spectrum. You find out the gamma rays at one end. That is at one end. That is a higher energy end. Gamma radiation has more energy than X-rays. When you pass gamma rays into tissues, they will penetrate through. X-rays, when you pass through the flesh, they will penetrate the flesh. They will not penetrate the bones. So they have energy lesser than gamma rays. You know that wavelength is inversely proportional to energy, and larger energy means shorter wavelength, smaller energy means longer wavelength. So the gamma rays have huge energy and they have shorter wavelength. X-rays follow that, and what comes next to that is ultraviolet, visible, and infrared region. Something in between the visible region and the infrared region stands near infrared region. And this region of the spectrum is so interesting. Ultraviolet rays, of course, are harmful to the human skin. Why are they harmful to the skin specifically? We are much talk about the skin cancer due to exposure to ultraviolet radiation. Why? You have a guess? Because the melanin absorbs the ultraviolet radiation, and ultraviolet radiation does some damage to the skin. And the ultraviolet range again is extending from 200 to 400 nanometer, and what comes next to that is the visible region that extends from 400 to 800 nanometer, and between 400 to 800 nanometer stands the entire visible spectrum: violet, indigo, blue, green, yellow, orange, and red. Red comes at a longer wavelength, meaning that they have a smaller energy. Infrared radiation, so that's why they are used for heating skin, heating flesh. They give infrared treatment for a better blood flow. And near infrared radiation is suitable for application in biology. These are all fundamentals, you know. The speed of light is related to frequency and wavelength. The visible region goes close to 800, and above that comes near infrared radiation. And these are all the wavelength ranges of violet, blue, green, yellow, orange, and red. One thing we should know, the color absorbed is one energy and the color observed is another energy. The complementary color is seen. Assume that there is a bottle containing a solution, it is red in color. The solution is red in color. What color it has absorbed is the cyan color. The cyan color, you see, that is just opposite to that. Cyan color means that wavelength corresponding to cyan is absorbed and that wavelength is subtracted, and what you observe is red color. If it is magenta wavelength absorbed, what you observe is green color. If the solution is green in color, the magenta is absorbed. You understand? And what happens in organic molecules when ultraviolet visible spectrum is observed? Ultraviolet and visible are considered together. Ultraviolet is one range and visible is one range. For both analysis, you use one equipment. There are two sources, a deuterium source and maybe a xenon source. There are two lights that excite the molecules, and what happens in molecules is this kind of excitation. N pi star, pi star, N sigma star, pi sigma star. I will explain what are these. This is the instrumentation. The difference between the absorption spectrometer and emission spectrometer is that in the absorption spectrometer, there is only one monochromator. In emission fluorescence spectrometer, there are two monochromators. This is the basic difference. Okay. In absorption spectrum, in UV visible spectrum, the monochromator, the sample, detector, source, all are in straight line. And in the case of fluorescence spectrometer, there are two monochromators. Both the monochromators are perpendicular to each other. The detector and the source are perpendicular to each other. They are at right angles. It goes, hits the sample, come back to the second monochromator, and it passes through that, collected by the detectors. You see, these are all instrumentation, you know, you obviously can understand. I talked about the difference between the absorption spectrophotometer and the fluorescence spectrometer because people are often confused, right? And I talked about the various excitations. You look at this molecule, you may not be familiar with the structure of molecules, still you know that there are two double bonds. When there are double bonds, that means there is a sigma bond and a pi bond. Pi bond can exist only when there is a sigma bond already. Sigma bond is the bond in the single bond. If there is a double bond, there is one sigma bond and one pi bond. So the excitation occurs mostly from the pi bond. Both from sigma and pi bonds, excitations will happen. Electron will jump into the excited state. But the more probable excitation is the pi electron getting excited, and that is what you see here. The pi electrons are having higher energy. They are in a level that's up. It's above the sigma bond, and it goes to the pi star level. It could be pi star level or sigma star level, and the energy of excitation, the energy of absorption leads to excitation. You can call that as a energy of absorption or energy of excitation. The energy of absorption in the case of pi to pi star transition is smaller than the sigma to sigma star transition. So in molecules where the pi bonds are there, absorption occurs at a smaller energy, means longer wavelength. And what you see here is absorption at 220 nanometer to 22 nanometer. And what will happen if there is only sigma to sigma star transition? Assume that this molecule does not contain double bonds at all. Only sigma to sigma star transition is possible. Only sigma electrons are there. Bonds that carry sigma bonds only are there. So that is possible only the sigma to sigma star transition, and that is involving a higher energy. Sigma bond is a strong bond. A strong bond means the bonded electrons are difficult to excite. Pi bonds are found by the sideways overlap of orbitals. They are kind of free. So they are easy to excite. A little energy is enough. So for sigma to sigma star excitation, you need a larger energy of light, and that will push the absorption wavelength below 200 nanometer. Below 200 nanometer wavelength is not at all considered in the ultraviolet visible spectrum. Why? Because below 200 nanometer, oxygen and nitrogen absorb very strongly. And to record such bands, you require high vacuum conditions. That's why the region below 150 nanometer is called vacuum ultraviolet region. Okay, for UV region or vacuum ultraviolet region. And what is above 200 is obviously interesting, and that shows what kind of bonds are there, how many conjugations are there. Conjugation means the double bonds in alternate positions. If the double bonds are in alternate positions, the absorption is more and the spectrum shifts to a longer wavelength. And you find a second band here in this molecule. Apart from the pi star transition, there is n pi star transition. What is that n electron? N electron is called a non-bonded electron, the electron that is not involved in bonding. Where is the n electron? That is around the oxygen. Two dots you may find in textbooks. These are called the non-bonded electrons, and they are not at all involved in bond. They are lone pairs of electrons. They are lone. They are alone. They are not involved in bonding, and they are loosely bound, and the energy required to move them up, go to the excited state is little, and that's why you observe the absorption band in the longer wavelength. And you find the n pi star band here in this molecule because there is a double bond O. In the earlier example, I showed a molecule without any oxygen or nitrogen, which has a lone pair of electrons. Here you find oxygen that can have a lone pair of electrons. Two lone pairs of electrons are there. They get excited, and you observe the longer wavelength absorption band. So there are two bands here. In this molecule, what you see at the right side, you find again pi to pi star transition, n to pi star transition. This pi to pi star transition is interesting because that is arising at the longer wavelength. And when the complexity of the molecule increases, when there is more conjugation in the molecule, conjugation, I mean the double bonds in the alternate position. These are molecules that are used in organic electronics. People working in physics, hardcore physics know about that. And organic electronics involve excitation from highly conjugated molecules. What you see at the right side is a molecule with 4 rings. The first molecule is called naphthalene, pink color. The second one is called anthracene, and the third one is called benzanthracene. And more number of double bond means more conjugation, more electron density in the molecule, more probability of excitation, and that shifts the absorption spectrum to a longer wavelength. You find many bands here. They are actually not many bands. One band split into sub bands in the pi star transition. Even though it is a pi star transition, that is shifted to a very long wavelength, close to 500 nanometer, and that shows a difference in the color of the molecule also. And the probability of excitation is more in the case of the benzanthracene molecule. Look at this molecule. I showed molecules with only carbon and hydrogen here, and you find out aromatic molecule with nitrogen and oxygen, amino group and nitro group. NH2 refers to the amino group, NO2 refers to the nitro group. What is the difference between the first molecule and the third molecule? First molecule has NH2 group, the second molecule has NO2 group. The NH2 group molecule tends to push electrons into the ring. Nitrogen has a lone pair of electron, and that lone pair of electron tends to go into the ring through conjugation. The NO2 group, the nitro group, has oxygens which are electronegative. They tend to pull electrons towards themselves. And you find the electrons from the ring tend to get moved to the NO2 group. That is the difference between the NH2 group and the NO2 group on the phenyl ring. First one molecule is called aniline that contains NH2. The second one is called nitrobenzene that is having an electron withdrawing group on the aromatic ring. And something is there where the electron is pushed inside the molecule, inside the aromatic ring by the NH2 group, and something which is pushed out of that, pulled out of the ring by the NO2 group. And you can call that as a push-pull effect, push-pull molecule. And that is not much possible in the fourth molecule. You see the NH2 and NO2 group being in different positions. They are not exactly opposite in position. And that makes a difference in the absorption spectrum. Leaving out the first molecule and the second molecule. Look at the third and fourth. They are not much different. Okay. But just with the position, you find the difference in the absorption. That is the probability of transition. The absorption depends on the probability of transition to a higher energy state. How is it possible? When the electron density is spread throughout the molecule and when they are available for getting excited by the incoming radiation, the absorption will be more, and that is what is reflected in the absorption spectrum. Okay, so that is how one should discuss the absorption spectrum of organic molecules. That is how the molecules, the absorption spectrum of any material is seen conventionally. And what comes next is the absorption in nanomaterials. And here is where we have to write new science. We have to add more information to the conventional technique. We have to understand the spectroscopy in a different way. And here is where you find the fullerene molecule in solution. Fullerene is a carbon 60 molecule. I showed something like a soccer ball. And you find that difference in the color. And that again depends on the number of carbons in the material. Carbon here does not have any group. There is only carbon. Maybe one or two hydrogens at places, but it's fully carbon. Nothing but carbon. And that has difference in the color. And this is the absorption spectrum of carbon 16 fullerene. And you find bands. And how will you explain the absorption of this? You cannot explain the absorption based on the pi bond, sigma bond, or anything else. These are all conventional ways of explaining. And how to explain the transition, absorption in this molecule. So we have to look at this molecule in a modern way, the way which is different from the explanation you offer in the conventional science. Look at that, the absorption of fullerene, the absorption of carbon nanotube. They may be looking similar in one sense, but you find obvious differences in terms of the intensity of absorption and clear-cut bands in the case of carbon 60. So it's all about carbon, but there is absorption. What makes the absorption? And what changes the absorption position and the intensity of absorption? That's the question. The excitation in these molecules come from electrons that are in strained positions. The carbon 60, you see carbon has a tetrahedral angle in normal conditions. In sp3 hybridization, maybe in methane, the best example where you find the sp3 hybridization with bond angles properly at 109.5 degree, but that bond is strained. It is stressed and it is under strain. And in some places, some of the carbons are not there in the graphene or the fullerene. Some points carbon is missing. Anyone who is working in solid state physics knows that. Not every crystal is perfect. Perfection is unattainable is a physics law. If everything was perfect, the world would not have been interesting. This is a statement. Crystals have imperfections, and imperfect crystals are more interesting than perfect crystals. And this imperfection makes some places in carbon having electron mobile, and that is what is making the absorption in carbon 60 possible. The absorption depends on such conditions, and it again depends on the size. So when you talk about the absorption of nanomaterials, you start speaking about size. When you talk about the absorption of metal nanoparticles, on the other hand, here is silver nanoparticle covered by a citrate, sodium citrate, and you find the silver nanoparticles in metallic form. Ag0 refers to the silver metallic nanoparticles, and in case of the conventional UV spectrum, one equation is known to everyone. It is called the Beer-Lambert's law. Absorption is equal to epsilon CL. L refers to the thickness of the absorption medium. L is usually 1 centimeter. The cuvette is 1 centimeter. So usually you substitute 1. So absorption is equal to epsilon C. Epsilon is a constant molar absorption coefficient, you know. So absorption is directly proportional to the concentration. When you talk about the absorption in organic molecules, you talk only about the concentration of the molecule, concentration of the solution. The things are not that easy when you talk about the nanomaterials in solution. You have to talk about the my theory. That is what is new in the case of discussion of UV visible spectrum of nanomaterials. You find out E lambda is the extinction, and you have to talk about the areal density of the nanoparticles, radius of the nanoparticles. Remember, it depends on the size of the nanoparticles. By saying size, I mean the radius. The radius makes a difference in the absorption. And wavelength of incident radiation, all these are known. So the radius, the size of the nanoparticle plays a role. The dimensions also play a role, the areal density. So I should mention here, apart from talking about size, shape also plays a role. In case of metal nanoparticles, for instance, silver and gold nanoparticles, the electrons on the surface are kind of oscillating. You call that as a plasma, you know, surface plasmas. They are jiggling, electrons jiggling, not like they are highly bound in orbitals connected to the central atom. The electrons on the surface are a kind of jiggling. I call that as a surface plasma, and absorption comes through that surface plasma resonance also. When you talk about the absorption of nanomaterials, you have to mention the surface plasma resonance band, and that is what is actually giving color difference to these gold and silver nanoparticles. You can calculate the particle diameter also from the absorption spectrum. You calculate the concentration, the exponential of concentration you fix, and the absorption you substitute. You can calculate the diameter of the nanomaterial, the nanoparticle. This is the UV visible spectra of silver nanoparticles of different sizes. You find out the 10 nanometer size nanoparticle having yellow color and 80 nanometer having red color. You find out the absorption spectrum shifting from the shorter wavelength to a longer wavelength when the size is increasing. The absorption band is around 400 nanometer at one end. It moves up to 530 nanometer on the other end. Huge difference in the spectrum, 130 nanometer, just depending on the size. You don't add any molecule at all to that. You don't substitute that with any other stuff. You don't even talk about the surfactant when you talk about the absorption, unless otherwise it is aromatic molecule that is attached to the nanoparticle. Just the nanoparticle, just the metal, you don't have any difference in the composition. Just silver nanoparticle, and that gives you different absorption spectra depending on the size. This is the UV visible spectrum of gold nanoparticles. The spectra correspond to gold nanoparticles of different color. You find dark red color to pink color. It depends on the size of the nanoparticle, and you find shift in the wavelength starting from 10 nanometer size particle to 100 nanometer. You find the absorption from 530 going up to 580. If you are further changing the size, you will find a difference in the color of the particle also. It can be even moved to 650. I mean, moving from 580 to 630, close to 700, that makes you bring the spectrum of the particle close to the NIR region. When it is getting closer and closer to the NIR, visible and NIR region, they find application in biology. When a light is passed on to that, energy of light required is low, and the technology involves a minimally invasive biological application. And you can predict the geometry of the molecule also from the spectrum. How does the geometry affect the spectrum? You see, silver nanoparticles of various shapes. It's not just the size, but also the shape that affects the spectrum. And it's not just one wavelength. You find shift from 405 nanometer to 720 nanometer. This is a huge shift, moving from close to the UV region to close to the NIR region, through the visible region to the NIR region, near infrared region. And these are cases where we play with the size and shape of materials. So we handpick gold and silver, the best known examples and best explored materials employed in various applications. That's why we talk much about these. But consider preparing metal nanoparticles of many metals in the periodic table. Many metals are the transition metals. Their absorption will be obviously different in different shapes. The area of nanotechnology still remains much unexplored. Plenty of work have been done over the years, over decades, but still it's an open field where we can dive into it. We can nose dive into the pool of nanotechnology. It's an ocean of nanotechnology where we can explore and catch many fishes. You see, silver nanoparticles of various shapes I showed. See, this is spherical shape on the left side and prism shape on the right side. You find change in the color from yellow to blue. Means that we are covering the most part of the spectrum. Assume that you want to determine the aggregated state of nanoparticles. This is actually a problem with nanomaterials. They tend to aggregate. They have surface energy different from bulk materials, and they tend to aggregate. Aggregation changes the absorption spectrum. And what happens when the nanospheres, assume that one nanosphere joins with another nanosphere in the process of aggregation. That is called a dimerization, and you call that as a redshift. The spectrum shifts when two particles join together. What is the reason? You guess? Because the transition probability is more, the surface area increases. Okay, the transition probability and the area of absorbing material that increases. Not only the transition probability explains the intensity also. I'm talking about the wavelength. The wavelength again depends on the size. So size increase changes the absorption wavelength. So that can be understood from the recording of absorption spectrum. So that gives immediate observation of what happens in the solution. So this absorption spectrum, UV visible spectrum, is finding huge applications in the field of nanomaterials. See, aggregations in the case of metal nanoparticles, you find the aggregated state shows a broader absorption spectrum and a shift of wavelength. We find a change in absorption due to the change in the size starting from 5 to 100 nanometers. There is change. Okay. And that is all about carbon nanomaterials, metal nanoparticles, and another interesting class of materials is lanthanide. This is a periodic table showing the lanthanide elements in yellow color. This lanthanide elements, the lanthanide series is much interesting when they are analyzed for their absorption spectrum, because they have the F shells, F orbitals, F orbital having configuration from 0 to 14. Okay, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. This everyone should memorize. I ask my student to by heart these series. This is a very interesting series in the periodic table. They show characteristic absorption, atomic absorption, due to the absorption from the ground term to the higher term, the excited term. And you can explain the magnetic properties of these elements and the luminescent property of these elements, absorption properties of these elements based on these ground terms. Okay, and these are the ground terms of these materials. Okay, so they involve excitation within the atom of lanthanides, lanthanum, cerium, praseodymium, neodymium, and so on. They have characteristic absorption. So these elements have been used in organometallic complexes of various forms, various geometries. They are applied in various fields. Light emitting diodes in many electronic applications, displays, phosphorescent screens. In biology also, labeling molecules, these have been used. But the modern application in nanomaterials, nanotechnology requires to prepare them as nanoparticles. We prepare them as nanoparticles, praseodymium oxide or neodymium oxide or neodymium ferrite we prepare, and we analyze them. They show characteristic absorption. Especially they are interesting when they show absorption in the near infrared region. The absorption spectrum of these lanthanide elements is different from the examples we have seen in the earlier discussion. See, in the case of organic molecules, organometallic complexes are the metal nanoparticles. See, this is the absorption spectrum of lanthanide oxides and lanthanide fluorides. See, how many bands are there? All these arise because of the atomic excitations. The F orbital, the F shell is having 14 electrons, 14 possible electrons. That has room for 14 electrons. In the case of F7, there are 7 electrons, 7 single electrons put in the 7 shells. So the excitation probability is much more. The excitation to different levels is possible. If you consider the ground term itself, that electron in the ground state can get excited to excited states of different energies. That's why we observe many bands. Many bands are there means you can excite them at various wavelengths. See, from 250 to the NIR region and even to the IR region. They go even up to the infrared region. So they are useful for biological applications. You can use the second biological window. You call that as there are two biological windows ranging from 650 to 1000 and 1000 to 1500. These are two biological windows, which mean that in this region, if you excite the material, it will not hurt the tissues or blood cells or the melanin. So these are called biological windows. So there we can find applications. The advantage of using these lanthanide materials in the form of nanoparticles over using them as organometallic complexes is that the nanomaterials show strong absorption. The luminescence property is so sharp, and you find sharp burns in the case of nanomaterials. And when there is an organic molecule joining to these lanthanide elements, you find one more band, charge transfer band also. See, so many colors. Because the F orbital is many in number and they are tunable with attachment of ligands or using a certain wavelength, you observe different colors. In the case of lanthanides, lanthanide nanoparticles are preferred nowadays. That's why the metal nanoparticles remain much unexplored. Apart from gold and silver, platinum, and so on, you can explore them. Those who want to explore any metallic nanoparticle can get involved in studying them, and much of the applications can be derived just by studying the ultraviolet visible NIR spectrum. This is some work carried out in our lab. You see here carbon nanodots, the something in the bottle that is luminescing in green color, green region you see. This is the absorption spectrum. You find 430 is the absorption. What you see at the left side in the bottle, orange color, is a natural color of the carbon dots in solution. One cannot easily imagine carbon being in different color in solution. But this is carbon nanoparticle, much easily dispersible in solution. And when you are illuminating it, it shows green color. And green color is a bright color that is easily visible in cells, and that's what you see here. And the absorption spectrum you see at the left side. One spectrum refers to the normal carbon dots, and polymer coated carbon dots are also shown here in the inset. So that's all